Hello, everyone. Welcome to another episode of Science and Technology Q&A for kids and others. I see there are a whole bunch of saved up questions here. Let me see. All right, we have one here from Aaron. Does gravity's strength cause a fundamental limit for the size of a planet? What about a star? What about a black hole? What about a galaxy? What about the universe? Good question. So the answer is, if you have a certain amount of mass in a certain volume, gravity will produce some amount of compression of what's there. And for example, if you have a planet, there are pretty big exoplanets that have been discovered around other stars, but there's a limit to the size of exoplanet that one expects can exist. I don't know how, it's some number of times larger than Jupiter, but not that many times larger than Jupiter. And anything bigger than that will tend to turn into a star. And it will turn into a star because what happens is that the force of gravity will compress the material in the planet to the point where everything, the atoms are so squashed up against each other that they start to undergo nuclear fusion, which is the process that produces energy in stars. So basically what happens is, normally, nuclear fusion comes because two atoms, the nuclei of atoms, get crushed together to the point or crash into each other fast enough that they can merge. Point is, nuclei have protons and neutrons in them. Protons are positively charged particles. Neutrons don't have any charge, electric charge. And the protons in a nucleus are such that they have positive charge, and positive charges repel electrostatically. The electrical forces make like charges repel. So if you try and throw two electrons at each other, they will tend to they won't hit each other because they'll bounce off as a result of electrical forces. If you manage to get the protons close enough, if you manage to get them to within about the distance of a proton away from each other, then the nuclear force which holds nuclei together will sort of take over, and those protons will merge together and make a bigger nucleus. When that happens, they release energy. That's where the energy of stars comes from. And so in order to get the nuclei to be able to fuse like that, to undergo nuclear fusion, one strategy is you just make them go really, really fast. And if they going fast enough, their kinetic energy can overcome the repulsion energy associated with the electrical forces. That temperature is millions of degrees. And that's what people who are trying to do plasma fusion, for example, are trying to do, is to replicate what happens inside the sun, where basically the fusion is happening because there's a high enough temperature that the nuclei are going fast enough that they overcome the force of electrical repulsion and can fuse. So that's one way to get nuclear fusion, is you're just going fast enough that you overcome that electrical repulsion barrier. The other approach is to just be crushed more and more to the point where these nuclei are just by sort of the pressure of the environment that they're in, are crushed together to the point where they are close enough that they can undergo fusion. And that's what will happen as a result of gravity. If you have a large enough body and a small enough volume, the thing will get crushed by gravity to the point where eventually nuclear fusion will start up. And so if you have a planet that's much bigger than Jupiter, maybe, I don't know how much bigger, maybe 10 times, something like that, then it is believed to be the case that the sort of interior of that planet will be crushed so much that you'll start to get nuclear fusion. I mean, to give a sense of how much crushing there is inside a planet like Jupiter, the center of Jupiter is believed to be solid hydrogen, solid metallic hydrogen. Hydrogen is normally a gas, but under enough pressure, it turns into a solid and actually turns into a metallic solid. But so if you have a larger planet, it'll sort of have larger crushing forces and will start undergoing nuclear fusion and will turn into a star. Now, of course, these things are complicated because it depends a bit on what kinds of elements are inside the planet. A star like the sun is mostly made of hydrogen, which is what most of the universe is made of. But inside a planet, a planet that's been formed, when a star forms, the kind of heavier materials tend to go into this sort of disk of stuff that is around the star that's forming, and those tend to form into planets. And things like hydrogen, if the planet isn't very big, is much smaller than Jupiter, for example, like the Earth, most hydrogen that is separately a gas on the Earth, it all escaped the atmosphere. The hydrogen molecules go fast enough that they escape the gravity of the Earth and go off into space, which doesn't happen when you have a bigger planet like Jupiter, where you still can capture hydrogen. But in any case, the question of how a sort of planet-like thing can sort of get crushed and form a star depends on the thing called the equation of state for the material that the star is made of. The equation of state is a fancy name for telling one, if you try and crush something, how much pressure, as you try and reduce the volume, how much pressure will be generated. And that's something that one has to try to work out for different kinds of materials. It's very important if you're trying to make a nuclear explosion, for example, knowing the equation of state as you crush things to try and make a nuclear explosion is something. It's something you have to try to work out, because if the equation of state has the wrong form, so to speak, instead of you successfully crushing things and making something which will eventually get, for example, dense enough to undergo some kind of nuclear process, the thing will just bounce, and it will be as if the thing was collapsing and then it bounced and never got crushed to that high density where those things can happen. So what happens? Okay, so there's this whole series of limits of, if you are a star of a certain size, then different things will happen to you. There's a so-called main sequence of the evolution of stars over the course of 10 billion years or whatever, or some of them much shorter than that. The lifetime of a star depends on the mass of the star. So for a star of the mass of the sun, it's about a 10 billion year life cycle. For much bigger stars, there can be a much shorter life cycle, even down to a few million years. And there are stars which kind of go through this main sequence. There's this letters OBAF, GKM, I think. And the sun is a G-type star right now, a G2 star. And different stars go through, well, depending on their mass, but they'll go through this sequence of stages. And depending on the mass, the end stage of a star can end up as a white dwarf, a neutron star, or a black hole. And things can happen, like a big star can undergo a violent collapse process and make a supernova, which is a huge explosion. The nearest star to us, Betelgeuse, well, nearest star, that is a really big star, really big red giant star that will have a supernova is a star called Betelgeuse, which in the next few million years will probably explode. And and that's it'll make the night sky bright on Earth for a few days and things like that. In any case, there are, and I have to remember what the limiting sizes are for these things. The sun will turn into a white dwarf eventually. If it's not much bigger than the sun, a star not much more massive than the sun will turn into a neutron star. And I think it's 1.5 solar masses is the limit at which the end state of the star, when it loses the pressure that it gets from all those nuclear reactions that are happening, when that stops sort of keeping the star to be big, the star will collapse. And with the amount of mass that's in the star, above 1.5, I think it is, solar masses, it will collapse into a black hole. Now, is there a limit on, so there's a limit, is there a limit on the size of a star? The sun is a comparatively big star. There are a lot of much smaller stars that are kind of, that in fact are quite hard to detect. And even quite close to the sun, there are stars that were only discovered comparatively recently because they're so faint. Like, for example, the closest other star to the sun is Alpha Centauri, it's a triple star. It's about 4 light years away. There's another star, Barnard's star, 6 light years away, which is a very faint star, small, faint star. And there are other stars which, don't even have names. They're just catalog numbers, HIP something or other, which are really quite close to the sun. And the reason they were not detected until fancy, for example, spaceborne telescopes were available is just because they're not very bright. And so, and they're small and not very bright. So sun is a comparatively big star. Now, there are much bigger stars like Betelgeuse, for example. Is there an upper limit to the size of a star? I think there's a bunch of discussion about that, and I'm not sure what the answer to that is. My guess is that in the formation process for a star, there certainly is a distribution of sizes, and there is a tail of larger stars that go only up to a certain point. Now, why can't there be a still larger star formed? I'm not sure. I think that depends on the processes of star formation and the way that things clump together from gravity in the formation of stars. And that there are certainly parts of the universe visible in telescopes, which are sort of nurseries for stars, where lots of stars are being created from dust, for example. And I'm trying to remember, there are all sorts of limits and stability criteria and things for clouds of dust or clouds of gas condensing into stars. And perhaps from those, there is an upper limit, but I think it's mostly that there's just a distribution of sizes and that there's there isn't much of a tail by the time you get up to masses, much, much larger. I don't know what the largest ones known are, maybe 20 times, I don't know, the mass of the sun, but it doesn't get hugely bigger. Now, in terms of other kinds of things, in terms of black holes, when black holes can merge, a black hole, once it's formed, it forms this event horizon where the escape velocity is larger than light, the escape velocity than the speed of light. So things fall in, but nothing gets out of the black hole. And for example, there are places in the universe where there are binary black holes, 2 black holes orbiting each other. They gradually lose energy as a result of gravitational radiation, and they gradually spiral in. In the last few seconds, they produce an incredible amount of gravitational radiation, like the equivalent of converting the whole mass of the sun into gravitational radiation energy in a matter of a few seconds. And then you have a single black hole at the end of that, single spherical-ish black hole at the end of that. And that's what gravitational wave detectors detect. And we can now pretty much detect a black hole merger anywhere in the universe. And they happen like once a week or something, I think, right now in the universe. Now, the galaxies seem to have black holes at the center of the galaxy, which are like giant garbage dumps for material in the galaxy, and gradually more and more things are merging into this black holes at the center of galaxies. Like our galaxy has a black hole that has a mass of 100,000 times the sun, and one can expect that as galaxies get older, there'll just be more and more of the galaxy will be in the garbage dump, so to speak, of the black hole at the center of the galaxy. To my knowledge, there isn't an immediate upper limit to the size of that black hole. Certainly the equations of standard general relativity, and the same thing will be true in our physics project, are such that you can have a black hole of any mass. You can, in our physics project, there'll be lower limits on mass, but I think there isn't really an upper limit. You can have a bigger and bigger and bigger black hole, and it's just a black hole. It's not like something like it doesn't there's nothing for it to collapse into. It is already collapsed, so to speak. So now, again, in terms of galaxies, our galaxy is what, 100 billion solar masses or something, maybe a little less than that. It's 100 billion stars at least. So is there an upper limit on the size of galaxies? Our galaxy is also a fairly big galaxy. There aren't much bigger galaxies around. And I think it's like stars. There are processes that form galaxies, mostly in the early universe in the case of galaxies. And they come from kind of regions of the universe where it's a little bit more dense And so things in that region will clump into one galaxy, things in another region will clump into another galaxy. There's a distribution of sizes of galaxies, which I think just has a tail. I don't think there's a necessary absolute upper limit. I think it's just a question of the clumps don't tend to get that big. So in any case, so the question was asking about, is there an upper limit on sizes of galaxies? To my knowledge, there's no upper limit associated with can you maintain such a galaxy. There will be an upper limit in terms of what kinds of galaxies were formed in the early universe. And that depends on things about how galaxies were formed. And that's a complicated story. It's still not very well understood. If you have I was talking about how in the case of nuclei, they tend to repel each other because they have electric charges where like charges repel. In the case of gravity, everything has a positive mass. There aren't, so far as we know, negative mass things. Dark energy is an example of a negative mass thing. But in terms of ordinary matter, it's all positive mass, and all positive masses attract. So if you have a box of stuff that all has mass and has gravitational attraction, it will tend to clump together. Exactly how that clumping process works is really complicated and not well understood. The end point of that clumping process is probably that you just form a big black hole. But first you clump into one thing, and then you clump into another thing, and eventually everything just clumps together to form a black hole. But it takes a while. It takes much longer than the current lifetime of the universe for everything to have just landed up in black holes. And the process of getting there is complicated, where things will kind of sort of spiral around each other, and sort of the sort of rotational forces will cause them to stay apart, and so on. It's really a complicated story. And for example, the question of exactly what happens when you have these two things which are sort of gravitationally attracting, when they get really close to each other, what will happen? Will they merge with each other? Will they form a binary star system? How will it exactly work? This is very complicated. And so there's less understood about this process of sort of self-gravitating gases than might be. But that's what's important to understand in terms of the formation of galaxies in the early universe. The other thing is, when there is a slight density contrast, when there's one piece of the universe that's a bit more dense than others, the piece that's more dense is the piece that's going to collapse first and form a galaxy. And that depends on the sort of primordial fluctuations of density. And again, that's another complicated thing, not well understood, that it's believed that in the very early universe, there were kind of fluctuations associated with quantum mechanical effects, and that those got amplified to produce the fluctuations that eventually turned into galaxies when it got much bigger. In our model of physics, it works somewhat the same way, except that in the end, there is a discrete structure to space-time, and probably the very early universe started infinite dimensional, but still with a fairly small discrete object. And so what one might hope in sort of an interesting possibility, challenging possibility, is that there might be a signature in the current universe of the actual structure of that very primordial universe that consisted of a small number of discrete elements. Perhaps, I mean, one of the more bizarre things that could happen in the universe is it could be the case that there are sort of symmetries of the very beginning of the universe, which are still manifest in the universe today. So, for example, one of the absolutely bizarre things that could happen is, the universe could have had like the symmetry of an icosahedron or something. And it might be the case that, oh, well, we're off in some arm of the universe over here, but there's an identical arm of the universe somewhere else, because there was a symmetry in the very early universe. That's a possibility. It doesn't seem to be the case, but that is a possibility that is in principle out there. So in any case, the formation of galaxies and the size limits to galaxies are complicated by the fact that they depend on these primordial density fluctuations in the universe that are potentially left over from quantum mechanical effects or their analog in our models, as well as sort of the way in which gases are pulled together by gravity And that's a complicated set of behaviors. Now, the final question asked here was, what about the universe? Is there a limit on the size of the universe? Good question. Our universe right now has about 10 to the power 80 particles in it, protons and so on in it. Maybe about a little bit more photons than that in it. It's a little bit harder to count photons because there are some low energy photons that sort of almost don't count. But so our universe has a certain size. And could one imagine a universe that's much bigger than our universe? I think the answer is yes. And I think in our model of how things work, in the ultimate object that represents sort of all possible, that represents the sort of ultimate universe is this thing we call the Roolead. And the Roolead is this kind of entangled limit of all possible computational processes. And what we experience as our universe is a particular slice of the Roolead that we are kind of positioned to be experiencing, so to speak, to be perceiving. And for example, the way that we perceive our universe and things like counting the number of particles in our universe, well, it depends what we mean by a particle. If we look down at the level of the actual microscopic structure of space, which we believe to be discrete and to have all of these discrete elements in it, maybe at a length scale of 10 to the minus 100 meters or something like this, there's a lot of structure going on in that, in sort of the very small scales of the structure of space. Things like particles, like electrons and photons, are probably pretty big compared to the underlying structure of space. Those are the things that we, who are also pretty big compared to the underlying structure of space. I mean, to give a sense of scale, the length scale for the underlying structure of space might be, we're not sure of this estimate, but it might be 10 to the minus 100 meters. The size of the universe is 10 to the 26 meters. We are about a meter tall, give or take. And so we're much on the bigger end of things in the universe. There's a lot of room down below, so to speak, of much smaller things. So when we look at the universe and we say, oh, there's an electron there, there's a photon there, those are pretty big objects, probably, on the scale of the actual underlying structure of the universe. And those things are, so if we were a different size, for example, we might be sensitive to features of the universe which are on a much smaller scale. And so, for example, counting the number of particles in the universe, right now we say, oh, that electron thing, that's a particle. But some little feature of space operating down at a length scale of 10 to the minus 80th meters or something, we wouldn't say that's a particle because we have no awareness that that exists. It's just some little thing that's happening, which on our scale is all just aggregated together and we don't notice it. But if we were on a very different scale, we would potentially notice it. And then the count for the little critters that are, tiny compared to us, billion times smaller than us, that experience the universe in a different way, their count of the number of particles in the universe might be vastly different from ours. But having said that, just looking at the universe as we perceive it, there's the question, can we derive the number that the universe has 10 to the 80th particles in it? Interesting question. Is there a way of saying, well, we got this universe and not the universe that had 10 to the 10 to the 10 particles in it, or not the universe that had, only 100 particles in it? Can we derive the approximate size of the universe? It's an interesting question. And right now, I don't think we have anything to say about that. I think we don't know. I think that it is probably the case that thinking about kind of the way that you slice the Roolead for observers like us, there is a certain inevitability to the size of the universe, roughly, within huge margins of error. But that's as far as I think I can get with that. I think that the question of the question of the density of the universe, how much mass there is per unit volume in the universe, that is something which affects things like the universe starts off expanding, but if there's too much mass in the universe, then the gravitational effect of that mass will cause the universe to recontract again, things like this. So there are constraints of that kind, but there's no overall scale that says the universe should be this size and not smaller or larger. That's something that will be interesting to be able to derive from our physics project. We're not there yet. It's actually an interesting question whether, if we know the size of the elementary length, whether we automatically derive the size of the universe. I'm not sure. Good question. All right, let's see. Right, Socrates comments, internal gas pressure versus gravity are the two main forces for star formation from nebulae. Yes, indeed. Okay, there's a question here from Parker about what was the pressure of the early universe versus today. Looked at in terms of sort of ordinary physics terms, the universe had very high pressure. It had very high temperature, very high pressure. The temperature of the universe gradually decreases. I mean, in our models of physics, it's sort of the early universe was really a sort of hotbed of activity, and it probably had infinite dimension, infinite temperature, infinite density, a lot of infinite stuff. And as the universe expands, it gradually is a calmer kind of place. But, the universe, what happened at the level where we already have particles formed and things like this, there was a time when the universe was so small and so dense, and in our models so high dimensional, that all of the usual things we talk about photons and electrons, so you couldn't identify any of those things. By the time the universe is maybe, I don't know, a microsecond old, a nanosecond to a microsecond old, you can start to identify definite particles of the kind that we are used to. By the time the universe is a second old, a lot of kind of nuclear physics-y type stuff is beginning to happen. And you can really identify, nuclei and not the protons at least, and things like that. By the time the universe is 100,000 years old, atoms are forming, and with protons and electrons and neutral atoms are forming. But before that, it's still, things are sort of too dense, too hot for it to be calm enough for atoms to form. But nuclei form a few seconds after the beginning of the universe. You start to form nuclei. I remember correctly. Let's see. I could work that out. The temperature falls below an MeV or so. That happens at about, I think that happens about 1 second after the beginning. In any case, the thing that, and by the way, the measurement of time is an interesting question. I mean, that's time measured in sort of today's way of measuring time. Time in sort of what we understand now from our physics project, time is sort of the progression of computation in the universe, the working out of the next state of the universe from the last one, that succession of making a new state from the last, that's the progress of time. And so the question is, in a situation where, where everything's sort of infinite dimensional, infinite this, infinite that, our typical clock won't work quite the same way. We can count the number of elementary times that have been, in terms of a single place in the universe, how many elementary times, how many elementary computational updates have happened in the universe. But if we start saying, what's the relationship of that to other parts of the universe, the usual notions of time are going to get kind of messy. And that, by the time one's a nanosecond into the existence of the universe, all of that stuff has sort of worked its way out. And one's starting to be able to talk about, identify things like the things that we know from our physics today, and be able to understand what's happening. But anyway, in the pressure of pressure in the early universe was very high. Oh my, we've got a okay. All right, all kinds of different questions here. All right, there's one from Sudo. Can one stretch a vacuum beyond a breaking point, similar to how matter can be compressed beyond a breaking point that leads to a black hole? So, well, the vacuum is everywhere, and the vacuum doesn't have nothing in it. The vacuum is, in our models of physics, one of the most important features of the vacuum is maintaining the structure of space. You know, it's a funny thing. I discovered that Descartes, back in the early 1600s, had kind of a realization that is very similar to something that emerges from our physics project. He said he thought that the universe was full of little vortices that were all sort of interacting with each other. And he said, if there aren't a bunch of vortices between two places, there isn't any space between them. Those places have no distance between them. And so it is in our models of physics and in the way we think the vacuum works. There's all this activity in the vacuum. There's all of these pieces of this giant network that represents the universe are there. And it is necessary to have all that activity to maintain the structure of space. So there's always activity there. Now, when you say, well, how do I disrupt? What can I do with that activity? Is there a way I can sort of, pull that activity apart? It's a funny thing. When people were first understanding, and this is in the 1600s, people were first understanding the idea of a vacuum. People didn't understand the fact that a vacuum was the lack of molecules of a gas somewhere. And they had this funicular theory, I just learned about this, of the vacuum that involved, the vacuum is this place where there are by the way, people had a very bizarre view of how gases worked. They thought that a gas consisted of a bunch of sort of particles that were pushed apart by little hairs between the particles, as opposed to what happens actually in a gas. There's just motion of the particles, and them bouncing off each other is what keeps them on average a certain distance apart. People imagined that there were little hairs that would, so springs between these particles that would sort of keep the gas, that would produce what was called the spring of the air, would push the gas apart. And so when it came to the vacuum, they thought there was this funicular theory in which there were little kind of lassos that would come from the vacuum, pulling things into the vacuum, as opposed to the vacuum is just a place where there aren't molecules of air, and so the air is going to push out into that vacuum. So I think this idea of, well, how can you control the vacuum? Well, one thing you can do is you can say, I'm going to put down these walls of matter in the vacuum, and then what is the property of the vacuum between those walls versus outside those walls? There is a difference. It's a thing called the Casimir effect between of the structure of the vacuum between the walls. Now, it isn't. What's different is the quantum processes that are going on in the vacuum. These same things, which are sort of versions of the processes I'm talking about, which knit together the structure of space. In quantum field theory, there's also the idea that there are these virtual particle-antiparticle pairs formed. It's, I think, really the same thing as what, at a very microscopic scale, I'm talking about as knitting together the structure of space. But what happens is that the types of sort of particle-antiparticle pairs that can be formed are a little different between these two walls that you put in place and outside them. In this limited region, very low energy, long wavelength particles cannot be formed between those walls, but they can be formed outside. And that leads to the small force of attraction between, for example, two metal plates just put in the vacuum. But now, if you ask the question, can you sort of tear the vacuum apart? Well, a couple of things to say about that. So one very bizarre effect is a thing called autoionization. So what happens is, let's see. Okay, so when you have an atomic nucleus, it's a positively charged thing. There are electrons that are sort of floating around outside the nucleus. And according to quantum mechanics, there are certain discrete possible energy levels of those electrons. It's like imagining that you have a string and you're sort of keeping it stationary at the two ends, and you can pluck it and it'll have it'll bow out once or twice or three times or whatever. Those are like the modes of a string, and the same thing happens with the modes of the electron field in an atom. Okay, so when it comes to the relativistic theory of electrons in atoms, so most electrons in atoms are going at a decent fraction of the speed of light, but not really close to the speed of light. But it turns out if you have a nucleus with a very high charge, you will have electrons that are, in a sense, orbiting very close to the nucleus, going at a speed that is very close to the speed of light, and very bizarre things happen. So in the usual, just to fill in a little bit of technical stuff here, in the usual quantum mechanics that people will learn in college or something like that, they talk about the Schrödinger equation, which is the equation for non-relativistic quantum mechanics when things are going not close to the speed of light. And the usual theory of the hydrogen atom is based on the Schrödinger equation. There's another thing called the Dirac equation, which governs the quantum mechanics of electrons, even when they're going at relativistic speeds close to the speed of light. The Dirac equation, when it was originally developed in the 1930s by Paul Dirac, had a very bizarre prediction. It said that in addition to there being positive energy levels of electrons, where electrons have, this energy or double it or triple it or whatever else, there would also be negative energy levels for electrons. So that seemed very bizarre. What could that possibly be? And then what Dirac realized was that there is an antiparticle to the electron, the positron. Electrons have negative charge. Positrons have the flip around a positive charge. And what Dirac kind of imagined was that you could think about things as there's this kind of sea of negative energy electrons, and every so often there's a hole in that sea of negative energy electrons, and that's a positron, the antiparticle of the electron. Okay, so the Dirac equation talks about both electrons and positrons, and what happens is if you have a nucleus that is sort of pulling the electrons in really close, so they're going really close to the speed of light and so on, eventually, when the nucleus is small enough and has a high enough charge, it will make the electrons, it will effectively get to the point where it can start creating electron-positron pairs from the vacuum. So right now we have the largest elements, the largest atomic number that we have is what, 120 or so. I think it's been reached. They're very short-lived elements, but that's 120 protons in the nucleus. Okay, the exciting thing that might happen one day is when we get to 137 protons in the nucleus, because at 137 protons in the nucleus, you start to get this autoionization effect. And what happens is, it's not completely clear that it's 137 exactly. That's an estimate, and maybe it's a little bit bigger than that, which will be a kind of a downer because it'll take longer to reach. But what happens is that the lowest energy level of the electrons is actually pulled into that negative energy sea. And so what happens physically is that electron-positron pairs are formed, and essentially what's happening is that the electromagnetic field associated with that nucleus is somehow intense enough that it sort of has the energy that is needed to produce the mass of an electron and a positron, twice the electron mass, and make those things spontaneously start appearing. So what happens is that's essentially breakdown of the vacuum. It's explicit polarization of the vacuum. So by the way, I should say, when you put an electric field across the vacuum, you will get a phenomenon called vacuum polarization. Actually, there's another phenomenon that is related to that one that is also called vacuum polarization in quantum field theory. But basically what's happening is that in the vacuum, there are electron-positron pairs that are formed all the time. And when you have this strong electric field, the electron-positron pair is formed, and usually those virtual particles, they get formed and they disappear in a very short time. But with a strong enough electric field, you'll be pulling one of those particles fast enough that they can't recombine, and they don't, and so you actually get the production of particles. Now, what's interesting is that that phenomenon is basically the same as what happens in a black hole, except that in the case of a black hole, the particles are being pulled apart by gravity. In the case of an electric field, they're being pulled apart by the effect of the electric field. And so just like, in fact, with black holes and Hawking radiation in black holes, there's a similar effect with electric fields. that is, I think Julian Schwinger was the person who pointed this out, in the 1940s or 50s, I think, that a strong enough electric field will also start spontaneously producing particles. And it's all part of the same story as this autoionization story with nuclei and so on. But the end result, okay, so what happens? You've got this nucleus, it's producing this it's just spewing out electron-positron pairs. What actually happens? Well, what happens is you've got this positively charged nucleus and it's spewing out all these particles. What will happen is that the nucleus will get shielded by the presence of lots of additional electrons. So actually, the nucleus, which started off as oh, look, there's a charge 137 nucleus or something, it'll get shielded, and eventually its charge, its effective charge seen from a distance, will be lower than 137. You'll no longer get autoionization, and everything will calm down. But that's a case where essentially you get breakdown of the vacuum, where the vacuum normally just has, it's sort of as in some kind of equilibrium, producing these virtual particle pairs. But when you put an extreme enough sort of force on the vacuum, either with an electric field or with a gravitational field, the vacuum will break down in that sense. Now, in terms of doing something where you can like pull the vacuum apart, just like you might have something where you have, a piston or something and you're pulling a gas apart, we don't know how to do that for the vacuum. It is conceivable. Okay, so normally in the vacuum, there is actually a high density of energy in the vacuum associated with all these processes that knit together the structure of space, all these virtual particles and so on. It's like, okay, there's a high density of energy in the vacuum, but so what? Because it's everywhere and we don't notice it. We only notice the difference between the kind of communal garden vacuum and the vacuum with some particular content in it. So there's this zero of energy that gets reset, which is the sort of the energy associated with all these processes going on in the vacuum. It's a bit of a kludge in quantum field theory, actually, the way that that's normally done. It works in a much nicer way in our model of physics. It's the buzzword for what's done in ordinary physics is, well, one piece of it is what's called normal ordering, but that sounds very benign, but it's actually kind of a hack. Anyway, it's the thing that anyway, you get this kind of zero of energy that has been sort of reset by well, it's that vacuum is happening everywhere, so we can count that as a zero of energy. Okay, so there is a phenomenon that may or may not be real, the phenomenon of dark energy, and dark energy is a thing where it's something that is effectively negative mass matter, and it is something which, if it exists, can account for the more rapid acceleration that appears to be seen in the expansion of the universe. Because when you have positive mass matter, it attracts and it's all pulled together. But if you have negative mass matter, you get anti-gravity and things are pushed apart. Now, what that corresponds to in terms of our models of physics and things like that is dark energy corresponds to places where there is, in a sense, less energy in the universe and where there is, in a sense, less activity, less things knitting together the structure of space, but nevertheless, as much space as there was before. So that's the tricky part, that normally the sort of the amount of activity determines the amount of space. But this is a place where it's a more complicated thing because the amount of activity determines the energy density. The actual amount of space is determined by what that activity actually knits. And so that's how you get the sort of mismatch that can lead to things like dark energy. So that's the sort of closest to, you pull the vacuum apart, and what's left over when the ocean parts is something which has less energy that corresponds to dark energy. Let's see. Okay, so William comments on in quantum field theory and general relativity, the 0 point of energy seems to be arbitrary. Well, it's not arbitrary in general relativity. in the theory of gravity, the zero of energy is associated with the cosmological constant, which is a thing that you just sort of put in there in the equations, and it will determine the overall expansion rate of the universe. The point is that energy, you can say, well, we're doing everything relative to the zero of energy, and that works up until the point where you say, well, let's look at it for the whole universe. How much, what's the in terms of things happening in the universe? Yes, you can reset the zero of energy however you want, but in terms of looking at the cosmology of the whole universe, you cannot. Let's see. And William also asks, why is flat space the lowest possible energy state? That's an interesting question. Flat space is, okay. So what we consider to be flat space is somewhere where there is no gravitational field that we can tell. And okay, this is about to get complicated, because the I mean, I could give some very technical arguments for why flat space is the minimum energy configuration, but I'm not sure it's actually true. And I'm not sure we know it's true. And for example, one of the things that can go wrong with the universe is that it's unstable, that the configuration of the universe that we're in right now is just teetering on the brink. It's like you're boiling a pot of water and you managed to get it above 100 degrees centigrade, but there are no bubbles forming yet because the thing you're boiling it in is so smooth that there's no nucleation of bubbles. And it is hotter than 100 degrees centigrade, but it isn't to the point where bubbles of gas are forming, because bubbles of gas forming creates, you have a homogeneous fluid where everything's the same. When you form a bubble of gas, it's an inhomogeneity, and you can superheat the fluid to some extent without the formation of bubbles of gas, supercool it below freezing point, and you'll get a certain amount of you'll be able to go if you don't have any nucleation center, if you don't have any little piece of dust or something on which there's an homogeneity that starts to form an ice crystal, then you can potentially supercool it, superheat it, and so on. So one of the possibilities is we're living in sort of a superheated universe, and if something happens in it, it'll be unstable and suddenly it'll boil. And so, for example, one of the things I figured out years and years ago, late 1970s, is in the standard model of physics, the standard model of particle physics, it's a sort of a hacky story, but particles get their masses by interacting with this thing called the Higgs field, which is a thing that is believed to exist throughout the universe. And basically, particles get mass by the fact that as they move, they're continually interacting with this Higgs field. And that's sort of continually giving them, that process of interaction is sort of slowing down those particles and giving them a mass. And the amount of mass of a particle is just supposed to be proportional to the extent to which it interacts with this Higgs field. Okay, so it turns out that there are effects to do with virtual particles that affect the density of this Higgs field in the universe. And in particular, if there are particles that interact very strongly with the Higgs field so that they have very high mass, then virtual particle, antiparticle loops of those things being produced have an effect on the Higgs field. And if those particles interact strongly over the Higgs field, they can have a big effect on the Higgs field. Okay, bottom line story, if you have a quark with a mass of above maybe around 200 times the mass of the proton, you have the possibility to make the universe unstable. So when the top quark was discovered, mass, 175 times the mass of the proton roughly, it's kind of squeaking in to the region that I figured out ages ago leads to instability of this whole sort of house of cards that exists in the standard model of physics with Higgs fields and things. And so what would happen? So if in fact there is an instability, what that means is the current structure of the universe with all the masses of particles, the vacuum expectation value, the level of Higgs field that exists in the universe, all of that stuff will be a metastable state, something like a superheated liquid. And if there is a nucleation front, then the universe would just completely change its character. There'd be sort of a bubble formed in the universe, which would get bigger and bigger at the speed of light. And as soon as it hits some region of the universe, oops, electrons don't have a mass anymore, and this happens and that happens, and the whole physics of the universe changes. As an entity living in the universe, you won't know what hit you because the front of the metastability front moves at the speed of light. So you don't get to say, oh my gosh, it's coming, freak out type thing, because it's coming at the speed of light and no signal can get to it faster than it gets to it itself. So it's kind of actually it's sort of an interesting analog to the phenomenon, I should think about this, the interesting analog to the phenomenon of computational irreducibility, the fact that you sort of can't know what's going to happen faster than it gets to you if something is going at the speed of light. So yeah, so it's a few thoughts on that. And I don't think it's totally obvious that flat space is the minimum energy stable configuration. I think that's a thing. People have tried to derive it in even in discrete models, things like spin network models and things. In our models, I think we know. It's a good question. I'm not completely sure how. I think it's inevitable. Yeah, I think our derivation of general relativity also guarantees that flat space is the minimum energy configuration. Well, at least minimum energy configuration within configurations that aren't too weird. And in our models of physics, there can be things much more exotic than black holes that exist in the structure of space-time. And they're not yet well cataloged, and that's an important thing to get done. Let's see. There's a question here from Satoshi asking about any ideas about hacking nature to gain powers like infinite energy, travel faster than light. Do you think they're possible? Can we really hack the laws of nature? So the thing to realize is that sort of engineering and technology, it's all kind of hacking one's way into making use of the laws of nature to do things. And I think it's more a question of what one wants to do than what's out there to do things with, because one of the things is, like, once you have a universal computer, once you have something capable of being a universal computer, you can in principle do any computation with it. And so you might say, well, that's the end of hacking. But it isn't, because there's a sort of practical issue of, well, what computation do you want to do and how do you actually get to do it and so on. And I think one of the things that we discover about the universe and things in it and so on is that we're continually realizing that we can sort of access and make use of, for something we care about, more and more features of the universe. I mean, there was a time when electromagnetic radiation has been around since the beginning of the universe, but we only discovered how to make it into radio near the end of the 19th century. And so that's sort of a hack to the universe, is let's use electromagnetic radiation to send signals. Let's use this or that effect to do something that's useful to us. Now, there are things where we've said, oh, that's just impossible. And there's a question of how we can get around that. I mean, my guess is that things like, I don't know, energy use, for example, it's, it seems important to us today, given that we're still, physical beings running around, driving our cars, flying our planes, things like this. If we were, a box of disembodied souls sort of implemented in a digital format, I don't think we care as much about energy use, because we wouldn't need, we wouldn't probably need as much energy. And by the way, by the time everybody's inside that, that virtualized world, the notion of how fast time goes and, oh, we got to run the thing at a high clock speed and use lots of energy to do that. Well, it doesn't really matter, because whatever's going to happen, assuming that you get to hang out there for the rest of eternity, so to speak, what you're going to care about in your experience is how time passes for you relative to other things that you are in your domain of experience. And there's no absolute notion of that. But in any case, I think there are things where, the amount we care about it is going to depend on sort of what condition we're in, so to speak. And I do think that in terms of things like energy, I would suspect that there will be hacks, in quotes, whether it's, sort of tapping into the geothermal energy that's that the Earth has had for the last 4 billion years, and making use of the immense amount of heat that is inside the Earth, or whether it's figuring out how to slide one's way into being able to do nuclear fusion, or one of a variety of other kinds of techniques. I think it is quite possible that there will be a hack, in quotes, where one can just say, oh, solve the energy problem. That seems likely to me, actually. How long it will take and exactly what form it will be, I don't know. I mean, the fact that we can get energy by, burning oil that was sort of created in the Carboniferous period, a few 100 million years ago, and so on, by a bunch of trees coming onto the land and becoming fossilized, the fact that that works is itself an amazing hack. I think that there are things that sort of seem like impossibilities, like traveling faster than light. One of the things I realized is that in our model of physics, the problem of traveling faster than light is really, it's more of an engineering problem, because what does it mean to travel faster than light? It means in the structure of space, as space is normally perceived, you can't go in a certain region defined by the structure of space. You can't traverse that region faster than the speed of light. But it's the tricky thing, because sort of space is a dynamic structure. And so you can imagine that there are places where sort of there are pieces of what forms space, which if you could pick the exact right one at the exact right time, you could kind of surf your way through and go faster than light. The analogy is this: you think about a bunch of gas molecules in a room. Most gas molecules only go a millionth of a meter before they hit another gas molecule, and their direction is randomized. And if you say, how long does it take for a gas molecule to go from one side of the room to the other, it takes a pretty long time. One could tell that by, how fast does a smell travel through the air, so to speak. It's pretty slow. So that's because gas molecules aren't, even though each individual sort of run of a gas molecule, the gas molecule is going basically at the speed of sound, it keeps on hitting other gas molecules. And so it has this random walk that in aggregate goes very slowly. But if you could pick the exact right collisions to have, and if you kind of navigate your gas molecule, you could have it go at the speed of sound across the room. And so it is, I think, with going at the speed of light. If you could kind of navigate your way to picking which parts of the structure of space you attach yourself to, you can probably surf your way faster than light. But the problem is, sort of what's happening is that great big photon that's making the light has to just go according to the average structure of space. And what you'd be doing is hacking your way to something tiny compared to the photon that's sort of hacking its way through the microstructure of space. And the difficulty with that is, well, that's all well and good, but what can you actually put through the microstructure of space? You yourself, this great big thing that's made of, 10 to the 100, atoms of space or something, you're not going to fit through that microstructure of space. You might be able to send a signal, maybe, if you could find a way to sort of detect, to create that microstructure perturbation and detect it at the other end. But, if it's like, well, I'm going to get on the faster than light spaceship and go and hop to the other side of the universe or something, it's not going to be you that does that, because you don't fit, probably. You would be shredded into little your sort of micro pieces of space in order to sort of fit through the tunnel that corresponds to the thing going faster than light. That's my guess about how that will work. But there's there are things that are sort of, in a sense, logical and mathematical computational impossibilities that we won't be able to get around. So, for example, computational irreducibility, the fact that there are computations where to know the answer, you just have to do the computation. We don't get around that. If we did get around that, our notion, we just get around it by saying, well, we're changing our notion of time, because time is this inexorable process of sort of computing the next state of the universe. And if the next state of the universe can be computed more easily, in effect, that means there's less time that's elapsed. So this phenomenon of computational irreducibility, that is a sort of hard limit, but it is determined by, it sort of maps itself onto our perception of time. So I think there are things where it's like we're not going to be able to get around it, but by redefining ourselves, like redefining, how the passage of time works, or in the case of traveling faster than light, sort of redefining what counts as us and so on, yes, we'll be able to get around what are, in a sense, hard constraints on the structure of the universe. But when I say we'll be able to get around it, it's not really we that gets to do it, because it is an observer, an entity very different from us, that gets to be able to do those kinds of things. The us can't sort of fit ourselves into the structure of physics in a way that lets the us, as we are currently constituted, be able to do those kinds of things. Well, let's see, maybe one more question. Turbulent is commenting, you can travel faster than light if the space between you and your destination changes. Happens if the universe expands, and that's why we get measurements faster than the speed of light in space. Well, yeah, this is a complicated mess. There are all kinds of funky things that happen, but the speed of light is how much distance do you traverse in a certain amount of time. And time, I'm saying, is defined by this sort of progress, computational progress of the universe. Distance is defined in our models by this sort of hypergraph of atoms of space knitted together. And that hypergraph is maintained by activity that happens through time. And this question of sort of what's the amount of space that the activity can traverse in a certain time, it's a pretty detailed question. And even in standard general relativity, standard theory of gravity, there are complicated things. I mean, it's there are complicated definitional issues about what's a thing that an actual observer could really detect as traveling faster than light. Let me give an example. Let's say you have a flashlight, and it's a flashlight. Let's say it's a laser. It's powerful enough that you can paint it on the moon, that you can shine it from Earth, and there'll be a spot on the moon. Okay, you move that laser just a tiny bit on the Earth, the spot will move really fast on the moon. It might even move faster than the speed of light on the moon. But it's a whole complicated issue. When you move the light, and it's going to get to a different part of the moon. How does it, exactly who gets to see it when, and what observer who is in this position gets to observe this and that and the other thing? And it gets pretty tricky. And there are a lot of sort of almost paradoxes, like the flashlight at a great distance. And by the way, we see events, in telescopes, see astrophysical events, astrophysical phenomena, where it looks like there's a jet that's moving faster than the speed of light. But in fact, that's for this phenomenon, for the reason of this kind of, the flashlight is shining a very long distance, and you're seeing kind of the effect of the flashlight, but it's not that there is material communication from the first position of the flashlight to the final position of the flashlight, those are separate photons, so to speak, that went to the first position of the flashlight and the last position of the flashlight. It is our perception that there is a connection between the first position and the last position, but there's nothing that actually goes from that first position to the last position. So there are a bunch of effects in general relativity and the standard theory of gravity that work that way. There are all sorts of, warp bubble effects and all kinds of things like this that are essentially working by distorting the structure of space in that particular case in a way that makes it so that an observer, and where it's a tricky thing to assess what's the observer, what's a feature of the observer versus what's the thing itself and what's intrinsic and what's not. And that's something that it's a very subtle phenomenon. I mean, for example, with black holes, it took 50 years from the time when the basic sort of gravitational phenomenon that led to black holes, the Schwarzschild solution to the Einstein equations, was discovered in 1916, but it wasn't known until solidly into the 1950s or even 1960s what black holes were physically like. And it wasn't known, for example, that as you pass over the event horizon of a black hole, that you wouldn't suddenly, that everything wouldn't, if you're in a spacecraft and it goes through the event horizon, you actually don't notice that. The event horizon is merely a mathematical thing. The only thing you notice is that if you won't get that if you send a signal out, that signal, you'll never get a conversation happening with anybody outside the black hole. Your signal will take, in a sense, an infinite time to reach somebody outside the black hole. And even though they could preemptively be sending you, hey, here's the next episode of that TV show, they can be beaming it to you, and that can reach you. If you say, hey, I want to stop watching that TV show, I want to watch another one, that message will never get to them if you're inside the event horizon of a black hole. But that wasn't known, that at the event horizon, your spaceship wouldn't be pulled apart and all kinds of other different bizarre phenomena. It wasn't known that that was a mere mathematical coordinate singularity until, well, 1940s, it was sort of known, but it wasn't really internalized until the 1960s. And so it's often very tricky to figure out, what's a genuine effect that an observer, okay, here's another tricky thing. You can have a theoretical observer who will notice some effect, but that observer isn't like us, so to speak. And so it's kind of like, well, that observer, which is the size of an atom, would notice this, but for an observer like us, we're not going to notice that. And so it's a really tricky thing to figure out in what, the underlying theory versus what we observe about it. So let's see, a couple of comments here and then should probably wrap up soon. Okay. William is commenting, you can't distinguish the geometry of empty space from one that has matter uniformly distributed in it. Yes, that is true. This is, again, another sort of can of worms about what can you observe versus not observe. I mean, if you have a spacecraft and it's going through that region of space and there are hydrogen atoms there, and your spacecraft is going at 99.999% of the speed of light, and it keeps on getting hit by, well, hydrogen atoms aren't so bad, but it keeps on getting hit by matter, then it's sure going to notice that it isn't just flat space. Now, one of the tricky things about uniform distribution of matter is like not having any matter there at all. Yeah, I mean, because there are things like particles, there isn't really a way to get a purely uniform distribution of matter. Now, having said that, things like the Higgs field are taken to be a purely uniform distribution of matter, although that's a hack, and it's really more of a mathematical construction than it is perhaps something real. But yes, yeah, well, Spare Parts is commenting, it's like you need to solve the puzzle of constructing the space you want to travel through before you can travel through it. Yes, that's absolutely right. If you could figure out, I mean, it's kind of like let's give an example. Let's say you've got a plane and it's flying through, it's flying through the air, and it wants to avoid that piece of turbulence. It could be the case. I mean, it might detect it with weather radar or something like this and just fly around it right now. But that's, in a sense, this is kind of like, to really be able to do that, the plane would have to make a plan at the beginning that says, I can compute the turbulence in the atmosphere, and I'm going to make a plan that to fly from New York to Los Angeles or something, I'm going to pick this particular route, which I can compute will not encounter any turbulence. Now, we can do that to some extent with weather forecasting and so on a large scale, but you can imagine doing it on the smallest possible scale and saying, yes, I can compute my path, and then it's going to happen this way. And so similarly, in the case of the structure of space, you could say, well, I'm going to compute my path and be able to sort of surf my way through the structure of space. I mean, it reminds me a little bit of, there are situations like submarines, for example, where it's like, well, you can go through water or you can boil the water, in which case you're not going through water, you're going through gas. And there are effects like that, or you can be producing, you can be putting out some kind of polymer that makes the friction between the skin of the submarine and the water go down, because it's kind of like a coating of the submarine where you get these molecules that go out into the water and cause the water to slide more easily over the submarine. And again, it's kind of like you're sort of building the environment that you're trying to travel through. And yes, that's ultimately what you would have to do to be able to sort of hack the structure of space to go faster than light, is you'd have to be able to know what is going to be at the next moment in time, what's going to change in the structure of space. Oh, I could bet on that, on going in that direction rather than in that direction, and then I'll be able to make the bridge to this other piece that will go like this, et cetera, et cetera, et cetera. Now, realistically, computational irreducibility completely bites you, but it isn't absolutely certain. Well, okay, it probably completely bites you, but it could be the case that just like there are particles like electrons and so on, there might be little space tunnels that get formed that form and disappear. But if you could just find those space tunnels, they might be at a very microscopic scale, and say, I'm going to go down this piece of space tunnel, this piece of space tunnel, and so on, then you might be able to kind of surf your way through the structure of space. All right, we've had a very oh boy. All right, one more physics question, and then I really should go. And another time we'll talk about some of the non-physics questions. Eggy is asking, why is the refractive index for X-rays smaller than 1? Don't know for sure that it is, but I'm guessing that that is, okay. The refractive index tells you when light goes into a material. Okay, when light is going through a vacuum, the usual picture is that there's an electromagnetic wave and it's just exists in the vacuum, and it doesn't require an ether. It doesn't require something like, like sound is compression and rarefaction waves in air. Light and electromagnetic radiation doesn't seem to require something like that. It can just be its own thing in a vacuum. Actually, in our models of physics, it doesn't quite work that way. And it does, in a sense, it is, in a sense, a feature of the structure of space. So it's going back to a theory which existed in the 19th century, really, of kind of that there would be an ether that supports electromagnetic waves. That theory went into disrepute because this thing called the ether drift was not observed in the Michelson-Morley experiment in 1900, and that was one of the stimulations for special relativity in 1905. But the fact is that in our models, in a very, very natural way, we sidestep the non-relativistic, the relativity breaking aspect of the ether, and we have something which is kind of like the structure that makes up the universe that does satisfy relativistic invariance. So it's one of those things where, in a sense, the model was rejected too early because people didn't see around kind of the structure of the model enough to be able to see that it was possible to take something like that. It's not at all in detail like the model from the 19th century, but the concept that there would be a thing through which electromagnetic waves travel like sound waves travel through the air. But in any case, the electromagnetic waves, light waves, X-rays, all those kinds of things, in a vacuum, they just do their thing. When they encounter matter, what happens is one atom will absorb the photon of light and then will re-emit it. And so when you shine a beam of light on a material, even a transparent material, what's happening is the photons of light are being absorbed by the atoms at the surface, then they are being re-emitted, and then they're being absorbed by the atoms one layer in, and it keeps going. It keeps on sort of passing the photon from one atom to another. In the case of something like a metal, you're stopped at the beginning. The atom is absorbed, and the photon is absorbed, and no new photon is re-emitted. But in the case of a transparent material, there are photons re-emitted. The thing is, there's a time delay before the re-emission happens. And that time delay causes light to travel more slowly in that medium. Like in glass, it travels 1.5 times more slowly than a vacuum. In water, 1.33 times more slowly, and so on. And that's happening because when the photon is absorbed into the atom, it takes a little while. The photon absorption causes an electron in the atom to go into a higher energy state, and it will then go down into the lower energy state. But that whole process takes a little amount of time. And so that's what determines, in a sense, the refractive index of the material, that time delay. Okay, so now, humph. What happens is, it's a little tricky because am I going to be able to explain this? I'll just say the sort of technical way it works first. If you ask the question, okay, let's say you have a beam of light, and that beam of light is a piece of electromagnetic radiation, and the electromagnetic radiation is a wave that has a certain frequency. So what's happening is, at this moment in time, the electric field is in this direction. A billionth of a second later, the electric field is 90 degrees away, and the magnetic field is in that first direction. That's kind of how an electromagnetic wave works. Just like a water wave, at this moment in time, the water is up, at the next moment in time, it's down. The electromagnetic wave, the electric field is in a certain direction, the magnetic field is in a certain direction, and so on. And that's how you make an electromagnetic wave. Now, what's happening then is you make an electromagnetic wave, you shine it on a material, so to speak. And what's happening is, in a standard electromagnetic wave, there'll always be another wavefront. It's just like there's the wave goes up, goes down, goes up, goes down, electric field, magnetic field, whatever, just keeps going. And it's a kind of continual train of waves, so to speak. And so then you can ask the question, when that train of waves goes into the material, what happens to the phase of those waves? So in other words, is it the case that those waves are, you're making it so that when you've got these waves, you might see them on the surface of water, for example, and then the water goes into a different region, let's say that's a shallower piece of the harbor or something like that, and the water waves can change their character, but they'll have the same frequency potentially. They'll still be being driven at the same rate, but the distance between the wavefronts might change, and that distance between the wavefronts will affect that's like determining some kind of effective speed for the wave. So to be mathy about it, there's a thing called the phase velocity, which is omega over k. Omega is the frequency, k is the so-called wave number, which is the inverse of the wavelength, and omega over k has the dimensions of a speed, and it is, if you count the frequency of the wave, how often it's wiggling up and down, and you look at the distance between wavefronts, but then that gives you one measure of the quote speed of the wave. But it's a measurement that is something that once the wave is sort of, you have an infinite train of waves, that's you're sort of measuring how that works. There's a different measure of kind of speed of waves. It's called the group velocity, mathematically it's d omega dk. The derivative of it's the slope of the omega k curve, and that basically tells you if you have a packet of waves that might be, if you were a bit of information in a fiber optic cable, it might be there's a 1 bit that's there, and then there's another one that's a 0 bit that's there. It's a big kind of clump of waves. It's not a continuous sequence of wavefront, wavefront, wavefront forever. It's a clump of waves together, and it's like there's no waves at all, and then you have this clump, and that represents a 1. It transfers information. So the usual kind of calculation of sort of what happens is, and sort of transmitting information is to do with group velocity. And the group velocity is never bigger than the speed of light in anything we've ever seen in the universe. The phase velocity, as kind of a mathematical trick, can end up being larger than the speed of light, which means the refractive index can be less than 1. And that's that's how that works. So I think I don't know it I should know this, but I don't know it. I think what's happening is the phase velocity is larger than the velocity of light, but it's just a mathematical trick. It's not something that is actually capable of transferring information, so to speak. So anyway, I better go get back to my day job here. But thank you for a lot of interesting questions, and I see a lot saved up for another time. I think there were a lot of some about biology and some about technology, and this is always fun for me. The terrible thing is that even subjects that I think I know pretty well, I realize as I try and explain it to you all that there are little rough edges, and I try and smooth them as I explain these things, and those help me a lot in understanding things better. And I really appreciate the questions that stimulate that. Okay, off for now. Thanks very much. Bye. See you another time.